Hello students, today we are going to look at the last question of the cache working, basically what to do on a write. So if you're thinking how are writes different than reads, there are a couple of points that I would like to touch upon here. The very first point is the number of writes are uh, very less when compared to number of reads in a typical program. Uh, and the numbers say that usually there are 80% of reads and only 20% of writes. In addition, for the instruction cache, there are only reads because we only read the instructions. And when it comes to the data cache, like I said, it can be 80-20%, and a more common thing is for every 2 reads there will be only 1 write. So whatever we uh, design the cache for is keeping the reads in mind. So this is more like the design for common case scenario, right? So everything is optimized at the hardware, keeping reads in view. We want to speed up the reads, or we want to reduce the power consumption of the reads, etc. Also, another point to add is writes are never on the critical path. What do you mean by critical path? Is that some action is waiting for the write to happen. So that is never the case. Processor never stalls on the writes because the store instruction is never a producer, it's always a consumer. And in addition to this, we can deploy what's called as a write buffer. What it means is, let's say we have the typical uh, memory address register and memory data register. For simplicity, I put as MAR only. So it gives us address, and the data cache replace it with data. So for the load instruction, it will reply with data. For the store instruction, it will consume the data and write it in that particular address. When we employ write buffer, situation is slightly different in the sense that we do not need not have a direct path here. For the loads, we still use the direct path where the data cache gets an address and it replies with the data. But for stores, we can employ some additional storage, small storage, probably 4 or 8 or 16 in capacity. It will have the address and the data that needs to be written. So all the stores can typically go to the write buffer, and the write buffer, as the time passes by, will accumulate some writes, and eventually when the write buffer is full or near to the full, we can start writing them to the data cache, or whenever the data cache is free, we can start writing the stores. Why this is done is so that the reads are given higher priority whenever a load instruction comes, and let's say in the very next cycle, or a store instruction also comes to the data cache, we do not want to delay the load instruction further. So this situation gets even more trickier when we are looking at some uh, more complex designs like the superscalar pipeline or out of order pipelines, etc. In Also, the write buffer can help in one other situation where we have a load request, and that load request is same as the address is same as the store which has come just a while before. What happens then is we can check the write buffer. If there is a hit in the write buffer, then we can supply the data to the processor right from the write buffer itself. We need not even go to the data cache. But again, for performance reasons, we access both the data cache and write buffer in parallel. But because write buffer is small in size, it is faster in response. The third factor is for reads, both the tag array and data array are accessed in parallel, because speed is of highest priority. And for writes, we can wait till there is a tag match. Why to read unnecessarily all the data arrays, right? Only if there is a tag match, then that particular way can be read from the data array and the data can be returned to that particular location. So writes can take lesser power when compared to reads, and they can take longer time. We can afford that extra time because there is nothing pending on that write. So in general, for writes we have more flexibility because they are fewer in number, they are never in critical path, and they can be slowed down. So with these in mind, let's look at what are all different design choices that we have. The first decision that we need to make is about the write policy itself. There are predominantly two write policies, which is write through and write back. And the second design decision is write allocate policy, which is write allocate or no write allocate. These write allocate policies will come into the picture when we have a write miss. It means that we have a store request from the processor and we found that the address is not present or the block is not present in the cache. What to do at that point? And these are write request. So we can term it as a write miss. So let's look at each of these policies one after another. We'll start with the write back cache. What write back cache does is whenever a write request comes to one level of cache, it will be written only in that level. So if you imagine there are three levels of cache, for example L1, L2, L3, and there is a store request from the processor, it will go to the L1, let's say it is a write hit, and the data will be updated only in the L1 cache. The updated data will not be seen by L2 or L3 or even the memory. So when will they see the updated value? Only when the block, this particular block gets evicted from L1 cache. So if L1 is a write back cache, writes to L1 will affect only the L1 cache. L2 will be updated only when this particular block to which data was returned to earlier is selected as a victim and is evicted from L1. Now, how to identify a block which is written and which is not written? So accordingly, we need to introduce one more status bit along with the tags, which is called dirty bit. So we already saw the valid bit, then the status bit of to maintain the recency information for cache replacement, and here is one other uh, information that we need to maintain, which is the dirty bit. If the dirty bit is set to 1, it means that this particular block was written to. So when this block is selected as a victim, the cache controller will check the dirty bit. If it is 1, then it will forward this data along with the address to the L2 cache. It means that the L2 will get a write request. If the dirty bit is 0, then it is a clean block and we can simply discard it, meaning that both L1 and L2 are having the same data. What are the positives of this write back cache? Is writes are handled within this level, hence they are in general very fast. Multiple writes to the same block will be absorbed by that block in that level. We don't we will not generate multiple write requests to the next level. So let's say for some particular block there are 10 write requests, all of them will be handled by L1, and only when this block is evicted, the L2 will be written. So L2 is effectively seeing only one write and L1 has seen 10 writes. Accordingly, this write back cache uses the bandwidth between L1 and L2 very less, and whatever available bandwidth is there can be used more for the read requests. Also, because the data movement is less, the power consumption is also less when compared to write through cache. Now let's see what write through is. As the name says, we are going to write the data not only in this level, also to its next level. Now, in the previous example where we had L1, L2 and L3, if L1 is write through cache and L2, let's say, is also write through cache, and L3 is, let's say, write through cache, whatever the processor has written to L1 as a store request will also go to the L2 as a write request, and because L2 is also write through, it will go to L3, and because L3 is also write through, it will go to the memory also. In each level, the data gets updated and it will also be forwarded to the next level. Now, if we have a case where L1 is write through, L2 is write back, and let's say the remaining levels or whatever, write through or write back, doesn't matter. If L1 is write through, all the writes, all the store requests which are writes to L1 will be seen by L2 also. But because L2 is a write back cache, only upon eviction of dirty blocks, L3 will see the writes. So each level of cache can be configured differently. So in a write through cache, upon a write, data will be written both to this level and the next level. Like I explained, if L1 is write through cache, all the writes will be seen by L2 also. In that case, the data in L1 and L2 are always in sync, we can say. So this helps in few things. It is much easier to implement than write back caches because we need not maintain any dirty information, and during eviction there is no extra uh, work to be done. The cache is said to be always clean because both L1 and L2 have the same data. And one case that can happen in a write back cache is, let's say there is a read request to L1 and that is a miss. So the read request is forwarded to L2. In the meantime, the cache controller of L1 will look for a victim candidate, and if it so happens that the victim candidate is dirty, what does the L1 cache controller do? It will generate a write request to L2 with this victim blocks data. So L2 will see both a read request and write request at the same time. This can potentially have some impact on the read latency, but because we employ write buffers and in general we prioritize reads, this need not affect the read request much. And given that the next level of the memory is always updated, write through cache helps to maintain what's called data coherency. Now, data coherency is a totally new concept. I have not spoken or discussed about it till now. I'll just give a one-line explanation. Let's say we have multiple cores and all of them are sharing the cache or the memory. If some particular core writes data to a location and some other core wants to use that data, if it is a write through cache, then the common cache will always have the updated value, so the second core can take it from that cache itself. Otherwise, it needs to talk to the first core, and then the first core should respond with the updated value, which is time taking process. Okay, this comes under the data coherency. What are the negatives of write through cache? In general, its bandwidth utilization is higher, and also because the total number of writes seen both by this cache and the next cache are higher than write back cache, it will consume more power. Oh, sorry. The total number of writes seen by L1 is same whether it is write back or write through, right? Only if it is write through, L2 will also see the same number of write requests. That is the reason there is a more power consumption there. Coming to the write allocate policies, like I already mentioned, these come into the picture when the write request is a miss in the cache. Now the question is whether I need to allocate space for this write in the cache or not. In the write allocate cache, as the name says, upon a write miss, a space will be allotted for the block. What it means is the requested block will be brought from the lower level of memory, written in its allotted place. Upon that, the current write request will be written. So the process which followed by the cache controller is more or less same as a read miss. Even for a read miss, we get the data from the lower level of memory and write it into the cache, and some part of it will be forwarded, let's say, to the processor. In the write miss case, for a write allocate cache, something similar happens. We look for the block. If it is a miss, it will be brought from the lower level, written into the cache, and then this updated whatever write value is there, that will be written on this block, and the block will be residing in the cache. When it comes to no write allocate, it is exactly opposite. Upon a write miss, what the cache controller will do is, it's going to say that I'm not going to allot space to this particular block, and it forwards the data and the address to the next level directly. So the contents of this level of cache will not change upon a write miss for a no write allocate cache. Now, when do we prefer write allocate to write no allocate or no write allocate is if some data we are writing to the cache we don't intend to reuse, then no write allocate is better because that space is saved in the cache and we can use it for some other important data. But if there is a case that write data that is written to the cache will be reused, then it's better to allot space to it uh, in this level of cache, and it can service more read and write requests at the later point of time. Now a quick example on how they can affect the uh, hit rate and miss rate. Let's consider a fully associative cache here, and let's consider a write back cache, and also assume that we have a cold start, meaning that all the contents of this cache are 0. Now let's say the sequence of accesses is something like this. We have a write request to location 100, then a write request, another write request to location 100, then we have read request to location 200, followed by write to 200, and then again we have a write request to 100. Now let's study each of those accesses in a because both the caches, either the write allocate and no write allocate, are starting cold. The very first request would be a miss in both of them. The very first request to this particular address 100. After that, the next write request is also for the same location. In write allocate, because we have brought the block with address 100 and placed it in the cache, the next write request will be a write hit. But in no write allocate, again it will be a miss and the write will be forwarded to the next level. The third request, which is read 200, it is a read miss in both of them. So the block is brought into the caches and uh, kept in the cache for any future accesses. Accordingly, the next write to the same location 200 will be a hit in both of them. And let's say the last access again is write to a location 100. This is a hit in the write allocate cache, but it will not be a hit in the no write allocate cache. So when does a write allocate cache is generally useful is when we have multiple writes to the same block, or we have one write and let's say following that we have reads to it. Basically, if there is a reuse of the data that we are writing, if we suspect that there can be reuse, then it's better to go for a write allocate cache. So in summary, we have seen write back, write through, write allocate, no write allocate caches, and we can design a cache either as a write back cache with write allocate policy, or a write back cache with no write allocate policy, write through cache with write allocate policy, and write through cache with no write allocate policy. So all the combinations are quite possible. But if we think about it, right, some of them will not make sense, and the normal caches that you see in any of your general day-to-day computing resource that you use, your phone or laptop or any server, either it would be a write back cache with write allocate policy, or it would be a write through cache with no write allocate policy. Why? Because if you look at the third choice, which is write through with write allocate, it doesn't make sense because all the writes are seen by the next level anyways. So what is the point of allotting space to this particular write on a write miss? And if we look at write back caches with write allocate and no write allocate, like I said, if we suspect a reuse of data, then it would be good to go for write allocate policy. Accordingly, we have write back with write allocate policy, uh, which is more prominent than no write allocate policy. So in general, because we have multiple levels of cache, L1, L2, L3, L4, even in some of the processors, each of those levels of cache can have a combination and any combination of this, and it is not dependent on any of the level which is above or below it. At each level, the optimization aspect would be different, and accordingly the choice we would go for would be different. With that, I will pause this lecture. The next lecture, we are going to deal with the performance aspect of caches. So far, we have looked at only the concepts, and next we are going to analyze how it can help us in terms of performance, specifically how these design choices can improve or decrease the performance of the processor. With that, I'll pause this lecture. Thank you.